Okay. Good morning, everyone. My name is, as we have said, is Chiwendo Emilia Madubueze. I'm actually a doctor. I'm not yet a professor. I just want to say thank you for opportunity to present. Thank you to Professor Augusto for the opportunity to present. It's an honor, a little me to present in the Guardian of African Society of Biomathematicians. I'm so happy to be here to see the prof, seeing all of them. I used to see their papers as a young researcher, to be in the same room with them. I am very, very grateful. So I want to present a work in Lassa fever, the Lassa fever virus, because doing this work in Lassa because it's something that I have in mind for so long to work on Lassa fever. And I know one or two persons like Professor Augusto will have an idea that always have interest in Lassa fever because it's a disease that is endemic in Nigeria. So it's ongoing work I did with some collaborators. You can see their name in the co-authors in this work. So thanks to all of them for being part of this project in Lassa fever. It's also ongoing work that we'll continue to work on Lassa fever. So I'm going to present towards ending Lassa fever and optimal control economic analysis approach. I'm going to look at optimal control, but before looking at optimal control, I'm going to look at some qualitative analysis of the model, the basic model, before we can go into the optimal control, look at the sensitivity analysis in order to look at what are the control we are going to implement in order to reduce Lassa fever virus disease in Africa, especially in Nigeria. So before I start that, I'm going to have just a brief of what Lassa fever virus is, which I know that most of the researchers, especially from Nigeria, have an idea of what Lassa fever virus is. Lassa fever virus is actually a virus that is endemic in Nigeria. We started in a town called in Bauchi State now, but it started in a town called Lassa in northern Nigeria in 1969. The Lassa fever virus has a rodent, which in form of a rat that is a natural reservoir of the virus. Now, the virus doesn't kill the rat, but anyone that come in contact with the virus can also die as a result of that. This virus kills up to 300,000 to 500,000 persons yearly. In fact, up to 300 to 5,000 persons yearly, resulting to 5,000 to 10,000 deaths. There is no vaccine for this virus for now. So, and also one thing about this virus is that the symptoms and signs of it behave more like other diseases, especially in the early stage of the infection. It behave more like malaria symptoms and typhoid symptoms, making it very difficult to identify at the earlier stage. So this virus can be transmitted in so many ways. This is what the rat looks like. It's a particular species of rats, which the mouth is much longer. So it's not the rat that carries this virus. There is a particular one that carries it. And this rat can shade this virus in the environment, where especially maybe it can infect food or things shade in the environment. So this virus can also be transmitted from rat to rat. It can also be transmitted to human, but the human transmission from human to human is very rare. Most times it occurs in the hospital, maybe due to not controlling infection control in the hospital. So then the symptoms of this virus are very, very similar with other diseases. First of all, initially when it started, it can be behaving like as if it's malaria or typhoid, but it can result in so many things if care is not taken at earlier stage. And 80% of people that is infected is asymptomatic, meaning that they are not aware they are infected. So making it difficult that the 20% that is already symptomatic may kind of find themselves in the hospital. And this particular disease can also cause this miscarriage to pregnant women at the early stage of their pregnancy if they are infected too. And studies have also it that people that recover from this virus, especially men, can still be infectious after 3 months of recovery. So this virus can also happen. It can also cause rashes. It can also cause bleeding. It can also cause diarrhea. It can also cause vomiting. And some of these things are something that are common to other diseases. Now, looking at distribution of Lassa in Africa, because this is Africa society, this is distribution of Lassa in Africa. You can see that it's also affecting other African countries, but more focus in Nigeria. This is Nigeria. So coming to Nigeria is almost like to cover almost all the areas in Nigeria. Looking at the map very well, this is a map of Nigeria. So the red, you see that the states that are affected with Lassa fever. Now, this is the cases that happen within 3 years. Now, when we look at this particular graph now, we can see that there is a periodic at one particular stage, one particular time in the year where this virus is mostly high. And most times we look at it during the dry season. We have 2 particular seasons in Nigeria. We have rainy season, we have dry season. And this dry season happens within November to April. So which we cannot really pinpoint whether, okay, is it the weather that is affecting it? Is it the time when people are preparing for farming work? So those are the questions that is open in Lassa fever research. So this is what cases within 3 years. So now, what we want to look at, what is actually causing this Lassa fever virus, because in a situation where they say the human-to-human transmission is very rare, and it's very rare for you to see rats coming to have a bite on someone. So we look at it, the environment may have an impact in transmission of Lassa fever. So what we want to look at this study is to study the impact of quarantine, contact tracing, and contaminating environment on the transmission dynamics of Lassa fever. Environment in the sense that because sometimes because you know how rat is very, it can be very smart. So it can actually have places to have a way of getting to human habitats, environments. It can contaminate food, it can contaminate in the way of searching for food to eat. So we want to look at the contaminating environment. Then we're looking at quarantine in the sense that people that is infected, if they can be associated immediately and kept treated immediately, because it will not reduce the contact with other people. So also looking at the contact tracing in the sense that if someone, especially those that are symptomatic, how can we trace these people that is asymptomatic? So in this work now, we are going to look at formulate a model where the human compartment is SEQIR, meaning that sustainable, exposed, quarantine, infected, recovery population, that the human compartment is divided. Then also, because the rodent is important in this dynamics, also going to consider the rodent population, which is susceptible, exposed, infected. Then we also have contaminating environment. Then also we're going to conduct a quantitative analysis of the model, then investigate the importance of the contact tracing, quarantine, and the elimination of virus from the environment. Then one of the most key of this presentation is to look at the economic ultimate control and economic analysis of this particular model. So this is the model flow diagram we have for this work. This is our SH is a susceptible human. We have exposed human. We have infected human. This is asymptomatic infected. S subscript SH is a symptomatic infected. We have quarantine of infected people, which can also use in another isolated human infected. They have recovery, and also we have people that has a contact with, like one of the mechanisms that some hospitals use is that when someone is infected, they try to trace the family of that person in order to keep them for a while and watch over them for manifestation of Lassa symptoms. So then also we have it that the people that recover from Lassa, it has not been established that they will not have it again. So we have it that people that recover can also move back to susceptible class. Now, then we also have it that the 2 infected humans are shedding this in the environment. Especially, that symptomatic person may not be aware that is infected. So they have a tendency of shedding this virus in the environment. And also the infected rat is IR. We have exposed rat and we have susceptible rat. Of course, we say that the rat does not die of the disease, so we do not consider death due to the disease here. Now, coming to the force of infection, in as much as we say the infected, human-to-human infected is very rare, but we cannot neglect that in the modeling of this virus. So we have it, there is a human-to-human transmission, which is beta HH. Of course, you have contact between the asymptomatic and asymptomatic infected. They also have rat-to-rat infected, because human-to-rat infected, in the sense that there is a tendency that someone can come in contact with the virus, maybe in the process of trying to chase away the rats or trying to eliminate the rat or thereabouts. They also have the contact with the environment, which also considered as the incident function, which has a carrying capacity of the contaminated, the bacteria in the environment, the virus. Of course, the same thing goes with the rats. We also have that the rodents can also, sorry, I don't know. So we also have it that rodents can have contact with each other. And also it can also contaminated, get infected through the environment too. In the process of searching food, it can also eat food that another rodent have infected. So now, there is actually a transmission, vertical transmission for rodent population, but we do not consider that in this study. There is also tendency of vertical transmission from human, especially from pregnant women through the placenta, but we do not consider that in this work because it's on a rare cases. So this is a model flow diagram we have. This is a model without the control. So being a system of equation we are using, well, of course, I mentioned that human population is divided into susceptible class, quarantine of susceptible people, exposed human, quarantine of infected people, asymptomatic infected, symptomatic infected, and recovery. So with this, we come up with a system of equation, ordinary differential equation. This is what our model looks like, which we can also have with the initial condition, being a system of equation, that we also have the initial condition supporting that. We carry out the basic properties of a differential equation, especially when it comes to disease modeling, in order to establish that each of these human compartments is positive, because we actually cannot have a negative human population. So we'll try to prove that each of the solution of that model system is positive. We started with the susceptible class. The same approach can be used for other classes, and we have it that our susceptible class is positive as far as time goes to infinity. The same can be used for other subpopulation, including the rodent population, including the bacterial populations. Now we prove the invariant region, the region where our model have to be particular. So we have that total human population. Total human population has to be within the births divided by the death rate. Of course, this is just because in a situation where there is no disease in the environment, it has to be the births and the deaths divided. The same thing go with the rodent populations. The proof of this is already clear in the main paper. So we look at Lassa fever equilibrium and basic reproduction number. Well, of course, the basic reproduction number is one of the quantities that we use in disease modeling to establish whether disease will die out in the population, whether it will remain in the population. It also helps us to guide if they are going to implement control or not. So this is what we have as our Lassa fever infected, Lassa fever and free equilibrium. So this is what we have our reproduction number, because the way the model is, so this is what our reproduction number gives us. So with this, we establish the local stability of Lassa fever free equilibrium when the reproduction number is less than 1. This equilibrium this stability is talking about is that as time goes on, provided the reproduction number is less than 1, the Lassa fever virus will die out in the environment. If all these parameters are in place and the reproduction number is less than 1, the disease will die out in the environment. But if it's greater than 1, then it's unstable. That means it may lead to an endemic situation. They also prove the existence of endemic equilibrium, which we have given as this. Although this, we can see that we have the force of infection in this equilibrium, this endemic equilibrium, because the model is more complicated. So the meaning of this solving is solved numerically in order to establish the endemic equilibrium states. And this is what each of these force of infection is given. So Then we'll try to prove the global stability of endemic equilibrium, which also we did in the original paper, in the main paper. We'll prove that the endemic equilibrium is locally stable if the reproduction number is greater than 1. But this happens is not part of a disease-free equilibrium state. So the global sensitivity analysis of the model is carried out for reproduction number in order to find out the parameter that drives the spread of the virus in the environment. And this is solved using a Latin Habicus sampling method and Pearson rank correlation. So this is more like we'll carry out a simulation for 1,000 runs in order to identify which of these parameters can actually that contribute to the spread of this virus. Now, the PRCC, which is greater than or equals to 0.5, absolute greater than or equals to 0.5, is taken to be statistically significant in the spread of the disease. If in a situation where we are plotting the scatter plot, you can see that you can see the direction of when it's greater than 0.5. It can actually show how the direction is going. So looking at this, we can see that the rodent parameter drives the spread of this virus. We see the contact between the rodent to rodent and the death rate of the rodent has a much impact on the sensitivity analysis, meaning that they drive the spread of this virus in the environment, meaning that if the transmission rate is increasing, it's actually going to increase the reproduction number, and that will increase the spread of the virus in the environment. Now, the same thing goes with that if more rats are killed, if more rats are being killed every time, it's also actually going to reduce the spread of the virus in the environment. So this showing that the environment doesn't have anything to do much with human-to-human transmission, but has to do with the rodent and the environment. So with that, we established the optimal control model. We use from the results from the sensitivity analysis, we established the optimal control model. So what we have here is the optimal control model. We try to look at 5 controls in this model. So what those controls implies is it's still the original model, but here we are including a control in our model now. Those control we are considering is vector control, which can be use of traps, rodents, roticide, and bats and poison. Of course, we know that trap is something that is very common in Africa to use about rats. So the second one is a personal protection, such as environmental sanitation, proper food storage, and rodent proofing. That's covering the food and environmental sanitation in order to drive rodents away. Then the third control we consider the quarantine rate of exposed individuals. Then the fourth one is public awareness, public education awareness. Then the fifth one, intensify disinfection of the environment. That's if the environment is infected, in order to disinfect the environment. So these are the 5 controls considered in the optimal control. So in order to do the optimal control, we have our objective functional we want to minimize. This is our objective functional we want to minimize, and which will consider those infected compartments as part of objective functional. Now we have our cause, which is given as y. 1/2, we have the first control, or each of the control squares. We are using square quadratic because of the nature of the control, also based in literature. So then our W1 is the weight function. W and A1 are the weight constants to balance the associated terms in the objective functions. Of course, we are doing this within a certain period of time. So from 0 to final time. So the time we can also determine in our simulations. So this also, we prove the optimal existence of the optimal control, which is also not in this slide. We also prove that in order to show that the optimal control exists. Then with that, we now carry out the analysis, the simulations. One of the simulation we did is do an efficiency analysis. This efficiency analysis is done to identify response plan that can prevent the largest number of infected individuals, regardless of implemented causes. So this particular analysis, what it does is that it took the total infected cases averted by the response, divide the total cases averted without the response. So what it means that if I'm taking a control, for example, one control, I'll take the total cases, divide it when that control is not in that particular model, and times it by 100. So this group, these controls were divided into 5. Because there are 5 controls, we have a single control response when only 1 control is implemented, double control when 2 are implemented, triple when 3 are 4, the same thing to the 5, the 5th one. So each of these control in each group, we carry out the efficiency analysis in order to identify which of these is more efficient. So when we do that, which have the details in the main work, we have it that in group 1 is the control of the quarantine that is most efficient in reducing the number of infected people. And the second one we have for group 2, we have it group 2, vector control and quarantine is the one that also reduce. The same thing go with each of these control. Each of these control, there is a particular combination that is more efficiency in controlling the spread of the virus, Lassa fever. So what it means that each of these control, this plot we have here is each of the control, each group, the one that is more efficiency in all of them. So also we carry out a Pareto analysis. This Pareto analysis is more like 80/20 principle. It's derived from 80/20 principle to identify the key risk factors. These key risk factors can be in form of response plans or population that contribute to most of the disease spread and control. So what this principle do is that this is the formula you use. You have to calculate the cumulative infection averted. And this is calculated by taking cumulative infection averted divided by total infection averted times 100. Is a percentage. So looking at this, if by the time we do our simulation, these are the infection averted for each of the control implemented. I'm using an example for group 1. For this group 1 now, infection averted is this. Of course, showing that U3 has more people that are averted from getting infected. Now we'll take a cumulative of this. Cumulative of this, that this is the first one. We arrange it in order of the highest to the least. So from what we have here, we now have the first one. Then we started adding each of them in order to have a cumulative one to the end. Then you will not carry out the cumulative infection averted to give us the percentage we have in the 4th columns. So from this, for us to know which of this is most, this is the example of the calculation for the U3. For us to know which of this is most important in reducing the infection and having more people averted from the infection, we have a plot here. We'll try to plot the graph. This is for response for group 1. In this group 1, we say it's 80 to 20%. So we are looking at the control that achieved the 80% infection averted. And if we look at it there, the control of U3 and U4 actually achieved that. But U3 have more higher number of people being averted than U2. So what it means that when it comes to group 1, 80% of infection averted is, because what we mean by infection averted, this is total infection here. So 80% of this total infection is what we are looking at for. So 80% of this infection averted is actually 2,225. Of course, there's 0.77, but because it has to do with human being. So the smallest one that meets this is U3 with an effective of 56.1%. That is this 52.1% that met it. Every other one, because that is one that has a higher number of people. Now, this is more like saying, okay, the one that has highest number of infection that is a cumulative infection. So also what it means that we can prioritize our plan, especially if we want control. If we want to implement only one control combination, we can prioritize, okay, we are going to carry out, we'll consider quarantine, which is U3, in order to reduce the number of people that is infected. Now, this is for this group 2, when 2 controls are implemented together. When 2 controls are implemented together, we can see that U1 and U3 are much in this aspect. So what it means that U1, which is vector control, and U3, which is quarantine, is also shown to be the most perfect combination to use when you are carrying out the Pareto analysis for group 2. And we see that the total infection averted in this case is going to amount to 8,180, 80% of it. Although the other plans are also good, but the U1 and U3 combination are the one that give a higher number of infection averted in this case. And this also corresponds to efficiency analysis that we also presented. So looking at that, They will also have for U4, U3 and U4, also having the same interpretation is also go with U3 and U4. We also have it in this case. We have it that for the 3 combination, the U1, U2, and U3 shows to be the best among all these. And coming to the 4 combination, the first bar is the one that shows the best among all of them. So what it means that for the group 3, the most effective response is from all of them that is above 80%. But in each of all of them that is above 80%, there's one that give a more priority cases among all of them, which is say is U1, U2, U3. The same interpretation can go for U4, for group 4. So after doing this, we try to look at, okay, since this combination of controls have shown that this is this and this and that, let's look at the cost. You can actually have a control that can actually reduce the number of people that is very minimal, but at what cost? Is the cost very effective to carry out? Because some control can be very effective, some control costs that are associated with them may be very high to implement. So we'll perform the cost effectiveness analysis to determine the most cost response plan among all the available options. We did this cost effectiveness for each of the group 1, group 2, group 3 to group 4. So what we did was we tried to calculate the average cost effectiveness ratio. We also considered the increment cost effectiveness ratio too. So this average cost effectiveness ratio is the ratio that compares 2 costs incurred for implementing a specific plan with the benefits obtained from the plan. So what this thing costs, the total cost pounded on a particular plan over total infection cases averted by that particular plan. So we have a cost divided by the plan. That is what will give us that. The same, so when it comes to the increment cost effectiveness ratio, we are comparing 2 plan. So we consider 2 plans between A and B, the total changing in their total cost over changing the control benefits of those response between A and B. So the lowest ICR, when it comes to average cost effective ratio, the lowest value is actually the highest cost effective when you carry that each of the group. Now, because we have 5 groups, we didn't put all of them here. We'll try to look at each of these for the group 1. For group 1, we have the response plan. The first thing, first of all, is that you have to arrange the infection averted in a descending order. So ascending order. So what happens in the number of people cases averted, you arrange in ascending order. The same thing with their causes. For the infection averted, that's how it will arrange. So calculating the assay, we see that this is what we have in our assay now. The lowest among all of them happen to be quarantine, which is U3, showing that the U3 is one that is most effective. But we also have to carry out the increment cost effective ratios. Now, to carry out the increment cost effective ratios, you combine 2 controls together. So what it means that I'm going to consider U4 and U1. I'm going to consider U4 and U1, combine both of them together. So for the U4, the total cost, because it's the first one, divide by this. For the U1, so it will now become the cost of U1 minus the first U4, divide also the infection averted. The same thing will carry that. When all these are calculated from this first one, this is how we got this result in the last column of this particular one. So when you look at that, you are comparing the first 2. Comparing these first 2, the highest among all of them have to be eliminated. So comparing 4 and 1, because 1 gave me the high assay that incremented cost effective ratio. So I'm going to eliminate 1 and then continue my calculation again for this particular one again. When I calculate the same to follow the same procedure that I have followed here, I can now see, okay, from this, I'm comparing 4 and 5, meaning that the 5 is higher than 4 here. Then I'm going to eliminate 5. Then I consider also continue the same process will continue until I get to this last 2. Coming to this last 2 now, I have 2 and 3. It means that 3 has the lowest value. So 3 having the lowest value means that 3 is considered to be most cost effective in this case. Sorry. 3 considered as most cost effective in this case. So coming to implementing one control, 3 shows to be the most cost effective in most cost effective control to implement when you considering only one control. And that one control in this case is quarantine in this case. So this is what for this particular group 1. Now for group 2, 3, and 4, we also the same thing will be carried out in the same thing. So in all this, we try to look at, okay, when we have done 2, 3, and 4, we cannot come up with for all the most, each of this particular group 1, the most effective, we bring it out. When the group 2 is carried out, is U1 and U3 that is most effective. When 3 controls are carried out, is U1, U2, U3 that is most effective. So bring all the most effective in each of these groups together. Now, we want to see in all of them, which of all these ones are most effective in general for the control of the virus. So what happens here, the same method we use in example we give in U1, the same method we are using for each of these one. Carrying out the same method in all of them, trying to look at, okay, if you compare this first one and the second one, the highest one will leave, which is the first one. The same thing go with each of these table. We end up with this last table here. From this last table now, we see that U1, U3 is the least increment cost effective ratio, meaning that that is the one that is most effective in all the combinations of the controls. So what it means that in all the controls, U1, U2, that's vector control and quarantine is most effective. But if one control is going to be implemented, quarantine is what from this study is given to be the most effective. If 2 control is going to consider U1 and U3, but in all, what is considered to be most cost effective from the analysis is U1 and U3, which is vector control and quarantine. Now, the vector control, of course, has to do with use of trap to reduce the rat population in the environment. So we can see that this also is U1 and U3 happens to be the most cost effective. And then looking at the most effective in all the group, we can see that it also satisfies the results we have in our pattern analysis and also in the efficiency analysis. So it to show us that each of these group are the one that is most effective to implement. When you are considering one control, when you are considering 2 control, which are the 2 combination of control will I consider? When I'm considering 3 control, which of the 3 control can I consider? So these are what this analysis is trying to establish in each of them. Then, so this is what we have so far in this work. Is ongoing work. We're still trying to look at other analysis because the work we did here, we did not factor in data, although we have data from we have the data for Lassa. So in conclusion, what we try to look at there is to highlight the key role of environmental contamination in Lassa transmission. We try to look at a model that integrates human and rodent population with contaminating environments. We also try to look at the optimal control and cost effectiveness analysis, considering 5 dependent strategies. Of course, we'll find out from our result that vector control and quarantine is most cost-effective approach to consider. So the work is ongoing work. We also try to look at what we are trying to do now is that we are trying to see how we can fit the model to data, although some work have been done in that. We're also trying to look at this particular model we have now, fitting the model to data. We're also trying to look at application of machine learning, especially physics-informed neural network to the Lassa fever model. Thank you very much for your work, for your time. Of course, one of the parts of this work is also already published in this paper. So most of the references are in this particular paper.